Welcome to today's talk in which we'll be looking at getting from concept to code safely and efficiently with model-based design. My name is Will Campbell. I am an application engineering team lead here at MathWorks for the group that supports our customers at the US government. I've been with MathWorks for the past 12 years, and in that time I have focused on our modeling and simulation solutions. So today we're going to be talking about model-based design. This is a phrase that gets tossed around a lot in certain engineering communities. And for those of you who are not in the know, it can often be confusing what exactly is being referred to when this phrase is being uttered. Funny thing is that even for those who commonly use this term, there are often wildly different opinions as to what exactly model-based design is. And so today we're going to spend our time looking into this term and getting a better understanding of it. The way we're going to approach this is we are going to start by giving a high-level overview of the MathWorks vision of model-based design, a vision that we have been supporting for about a quarter century now. From there, I will work through a state-of-the-art model-based design process using the latest technology. We will examine the different phases in a development cycle using MBD. I will wrap things up with a couple other items. First, we'll talk about variations of model-based design. Part of the reason there's some confusion as to what this term means is that there are different ways you can approach this in some different workflows. So we'll examine a few of those. And then we'll close by talking about ways you can learn more about model-based design and begin to become proficient with the technology. And with that, I find it's best to just dive straight into a problem to give you guys something tangible to wrap your head around these ideas. The problem we'll be working through a few times today to illustrate the concepts of model-based design is this one. We'll be looking at the development of a quadcopter like the one in the picture seen there. This quadcopter has a mission. Its job is to maintain an object within the field of view of a camera that is mounted atop this quadcopter. I imagine none of you are working precisely on a problem like this. However, what I like about it is that it is a problem of sufficient complexity to give you a sense to how model-based design can be seen in action. Because when you think about what's required to go from an initial idea to a fully functional quadcopter, there's quite a bit that's involved with pulling that off. How you would traditionally approach that is that you would begin by spelling out further details of what precisely it is you want. And you would turn to a requirements document or some other requirements tool to capture that. So we will take a look at the MathWorks solution here. What we have is the requirements editor. The requirements editor is a tool that we offer to you that lets you author and manage your requirements for your program. At the highest level, you might do something like define ConOps specifications. So what is the mission? What is the target that we're trying to go after? And what are the requirements on the system that we're trying to track? And from within here, in each one of these, and if you may have more, of course, you can go in and give it further information spelling out precisely what it is you're after. What type of requirement is this? What kind of tags or keywords do you have affiliated with it? You could write an entire essay here describing what this requirement is all about. And if you have elements of your requirements document that need to show linkage to lower level requirements or other requirements, that is perfectly doable in this system as well. So you see here, for mission duration, we know that the mission duration is affected by the performance of the aircraft and the scope of the power system. What we have here is a link that will take us from this section down into the other section, which describes the requirements on the quadcopter itself. I'm not going to look at aircraft performance right now. Instead, what I'll do is I'll look over the flight control system, which is a bit more fleshed out. And within the FCS, you'll find several different subcomponents. And like before, what you'll find is a link that drills down from now these requirements to further requirements that expand upon this idea. So that will lead us over here to FCS requirements, and then there's FCS modes. And at this point, now you have a new kind of link that we've not seen before. Yes, we can go down further into another section in HLR, but we have this other object over here which talks about implementation. So this requirement will map to a design artifact, our model of the logic of the system, or the mode logic. And what you have is a hyperlink that takes you over to a functional Simulink model. In this case, the Simulink model has a state machine at the heart of it. We can go inside of it, and I won't bother you with the details, but suffice it to say that this state machine's job is to ensure that all the different modes of operations that the requirements document said are required are implemented into the design. If you want to trace that, you can click this button over here. We can enter the requirements perspective, and we can see that not just that overall state machine, but individual transitions and other elements inside of this model have linkages back to specific requirements. In particular, this one here links back to requirement 51, which if I want to go see back in the requirements editor, I can do that here, and now we see the description of that requirement. Okay, so we have done this not just for this mode logic, but we've actually done this at the higher level quadcopter level. So this is an overall system of system simulation. We've got the vehicle combined with the object that we're tracking, a green ball. We have a simulated environment, the VR world. We have some video processing, which is done off board apparently. And then we have a ground control station. Suffice to say, there's a lot of details we'll come back and look at later. But for now, what you need to take away is that we have taken our requirements and we have converted them into a design artifact in Simulink. And now that we have it, we can begin to run our simulation. So I'll push the simulation button here. And we can see in our simulated world how our vehicle is performing. To do that, what I'll do is open up these two windows. So once it kicks off, what you'll see is the object has a prescribed set of motion in three-dimensional space. It moves about. The vehicle then takes off when it's commanded to do so, and this is where it looks like in our VR world, and this is its simulated understanding of what the camera is seeing. So the camera's job is to keep this thing in the center, and the green object keeps moving. The vehicle tracks it as best it can. Won't run it to completion because I think you get the idea. We would use this environment, now that we have it, to run a bunch of different scenarios, make sure that our design is satisfying the requirements we have asked it to satisfy. And once we're happy with that, we then may take components and begin to actually implement them on the vehicle. For the mode logic, the way we would do this is we would take this specific component and we would convert it into C code so that we can take this C code, put it on board the embedded processor, and see it running on the vehicle. So I don't have the vehicle here with me, and you won't be able to see it over the web anyway, but what I can show you is that we have already generated code for this chart, and I can show you the linkage from here at the design level down into the implementation level by taking any individual element inside my chart, right-clicking on it, and saying navigate to code. So this code was made previously, and we see here all these pink lines indicate that they are derived in part or whole due to that transition line that I navigated from. And on top of that, if we scroll to another portion, we'll see that not only do we have linkage between the design and the implementation, we also have linkage from the implementation all the way back to the requirement itself. So I can click that link, and it will take me all the way back to the specific requirement in our editor that this thing derives from. So what we have, in essence, is a digital thread. We can go all the way from our beginning ConOps specifications down to lower level requirements, trace our requirement into the design, then once we've satisfied with the design, implement it automatically and show how that implementation derives from design and derives from requirements. All one concise digital thread. And this is key because this idea of being able to show how you get from one phase to the next in your development process is at the heart of model-based design. So what we just saw were the artifacts associated with the left-hand side of a design V. The design V is a way of thinking through how engineers get from an initial idea to a fully functional system. You start on the upper left with your ConOps. Your ConOps inform the requirements for your system. Those requirements in turn inform the architecture. And once you have an architecture, then engineers can begin to work out the low-level details of the design for individual components. And once they've got a design in place, you can then implement that design and you work your way back up the right side of the design V. You integrate components until you've got yourself a working prototype. And once you have a prototype, then you go through some sort of test and verification process to make sure that you are satisfying the requirements you set out to satisfy in the first place. If all goes to plan, you've got yourself a working system, you put it out in the field. Now, for smaller programs, this process may be very informal, but there are many large programs that this development cycle is going to span multiple years for. There are going to be thousands of engineers working across multiple organizations on different pieces of this puzzle. It's very unlikely that any one individual will start at the top left and intimately follow through all these different phases of the design V. In that kind of situation, it becomes critical that you get the handoffs between teams right. What you want to do is you want to avoid loss of information, you want to avoid repetition of work, and you want to avoid inadvertent errors being injected into the system. This is a slide that captures a diagram seen from a 2004 NASA paper. And really what this is illustrating is the old adage that a stitch in time saves 9. You're looking at, on the y-axis, the relative cost to fix an error as a function of when it's caught and when the error was actually introduced. And the ironic thing here is that it's the most expensive to fix an error when you get into that prototype testing phase, right? It's much better if you catch an error that you've made earlier in a coding phase if you're working on software, or even better, the design phase when you're working at design details, or even better, way back when you're defining requirements. Now, in order to pull that off, though, it becomes critical that you have infrastructure in place that supports catching those errors. What you're going to need is you're going to need a design environment and a coding environment and so forth that is going to enable you to actually go through some sort of formal test and verification earlier in your development cycle. Not only will you need an environment that can do that, but you're also going to get more value out of whatever you do if those artifacts you're producing upstream are very tightly coupled with whatever's coming downstream. If my design is a drawing on a napkin, well, I don't have a very good way to test and verify that that's the correct design, and I don't have a very good way to transition that drawing on a napkin into functional software. I'm going to have an engineer read that napkin and decide how to code this thing up. It would be much better if I could more tightly couple those two steps in the process together. So lo and behold, that is really all of what model-based design is about. The idea here is that you want to center all phases of a design V as much as possible around a single design artifact, namely a model. This model will have items that derive from it. It may have things that connect to it, but everybody is using the model as a common framework to work off of. And by doing this, you make all these different phases of development more tightly integrated. And by making things more tightly integrated, you allow yourself to catch errors earlier, you allow yourself to make transitions between teams more effective, and ultimately you're going to get the same quality product or higher for less time and money. That's really what model-based design is all about. As I alluded to at the beginning, there is nothing new behind this concept of model-based design. It's been around for a very long time, and there are countless examples of teams out there being successful using this approach to save themselves time and money. Here's an example from BAE working on a software-defined radio project. You see that they moved to a model-based design approach, in this case using Simulink, and what they found is that their project development time was reduced significantly, 80%, as you see in the results there. So this case, I bring this one up because we're looking today at a quadcopter control problem in C code, but I thought this was a good way to highlight the diversity of applications that are out there, because you're looking in this case at a communications application using HDL code instead of C code. Now, of course, it's not just our industry in which this concept is being used. Yes, across aerospace and defense, there are many organizations that have been using this. Here are a few that have acknowledged it publicly. But it's also being used across multiple industries, like the other three columns indicate. Odds are that there is model-based design software running inside the automobile that you currently have in your garage. And there are many other applications that probably are using model-based design approaches that you aren't even aware of. So it's a very well-established process, and all these organizations would not be using it were they not seeing value out of what they were undertaking. All right. So as I said, that's my high-level description of what model-based design is. I'd like to now transition into that second goal of the day, which is to outline a state-of-the-art model-based design process. I will provide you a complete, robust idea of what is available, and then we'll talk about variations on that afterwards. So, what do we have? Well, in the Simulink toolchain, what you would have is that you would start with requirements. We already looked at requirements, the requirements editor during the Quadcopter example. You see that we have a tool that lets you author and manage requirements with a variety of different fields to help you define what it is you're looking to do. I will say that in practice, this is not what we commonly see engineers do, starting from a clean slate and working with our editor to write the requirements. Instead, what we see more regularly is we see that large programs are relying on third-party requirements management software, such as DOORS, to manage the overall requirements for the system. There may be many aspects of your project which never get directly involved with Simulink, and so it's important for those aspects of the project to have access to the requirements. And in many other cases, they're just people that are comfortable and experienced using a tool like DOORS instead of our stuff. That's fine. We have no problem with that whatsoever. In fact, we have a workflow that perfectly supports that, where what we do is, instead of authoring requirements in our editor, we import them from your third-party software. And at that point, what you're really getting is you're getting a middleman that allows you to connect back to your original source requirements, but also down into the lower level design details of the architecture and the design. This enables you to stick in one tool chain from requirements beyond and down further, and it avoids potentially cluttering up your third-party requirements management software environment. So again, a common way we see people approach this. But the key here is you can author and you can view and you can manage in our tools, and you can establish traceability up the chain or down the chain as needed. Now, once you have requirements, you can then begin to define your architecture. In this phase of development, what you're doing is you're breaking your problem down into explicit components, and you're establishing how those components relate or interface to one another. You are not going to the level of detail where you are spelling out explicit behavior for individual components. That is for the next step in the process. What you may do instead is that you may also give some attributes or additional metadata information to components in the architecture phase. You may say things like, well, the quadcopter is going to weigh so much, it's going to consume so much power, it's going to require so many man hours we estimate to work on the ground control system, and it's going to require this many staff. Some very high level definitions of what each of these components may be all about. Okay. So if that's what you're looking for, you will sometimes hear this step in development called model-based systems engineering. There is a tool that MathWorks offers. It's explicitly designed to address this phase in development. It's called System Composer, and you're looking at a screenshot of it over there on the right-hand side. It focuses on these component definitions, interfaces, and what we call properties. And if you build up this system in System Composer, then what you get is the ability to easily transition down into the components, which we'll take a look at in a moment. We have that traceability back to requirements through the linking we saw earlier. And you have MATLAB as a backend to query any property information you place on these components. So there's a custom API to examine these architecture diagrams you construct, and you can use those to query information and learn more about your system. It's handy for things like first cut optimization, trade studies, and the like. And with MATLAB, of course, you have all the power of analysis that you would need to pull that off. Like with the earlier step of requirements definition, there are other tools out there that we see teams use in the model-based systems engineering phase. If that is your workflow, what you can do if you want to maintain that other tool is you can leverage the API that we provide to import or potentially export information between the two of them. So often that is a custom process. We do have the ability to do it. Okay, so that is the idea. Again, it is called System Composer. It's an extension to the Simulink environment, and we'll take a look at that and show how you get from architecture in our tools down into design. So we'll jump back to the quadcopter, and what you'll see is that model I ran earlier in the talk. This was actually a System Composer diagram. We were able to execute it because we have lower level behavioral information specified for this model. The badge that you'll find on System Composer elements that indicates there's behavior is this little icon affiliated with Simulink. I won't go into video processing. Instead, we can drill down into the vehicle. You see it's comprised of a plant model representing the physics of the vehicle itself and the flight control system. We have interfaces here, but again, no behavior, just connections between things. Drill one level deeper, we are still in the same situation, but if we go down once more into the controls, let's say, now we've transitioned over to Simulink. And here we have the ability to actually put in some behavior. We have hard numbers, data coming in and out of this component. Those numbers are being put into specific blocks that are performing calculations on them. For instance, inside the position control, you'll see some math beginning to take shape. Okay, so the idea here is that we enable you to move from just specifying how things are connected to actually working out what they do internally. We are looking now at the traditional Simulink approach of making this happen. We have a very rich library for those of you unfamiliar with Simulink that enable you to go in and build a system of your choosing. Core Simulink focuses on what I call first principles modeling. So if you know the equations that govern your system and you want to mechanize them, you can do it graphically using blocks like the ones we see here. You can also get down to the point where you specify behavior as code. So we have the ability to integrate MATLAB code into Simulink models or code from other languages such as C and Fortran. Okay, so you kind of have the best of both worlds when it comes to graphical and text-based representations of behavior. If you would like, and you have a need to not start from scratch, just building up with things like multiplication blocks, we have a series of toolboxes and block sets that extend the capabilities of Simulink, provide you some starting blocks that are application specific. As an example, you see here the Aerospace block set, which focuses on blocks pertinent to aerospace applications. So if you don't want to build a digital DATCOM component from scratch, you can leverage this toolbox and make it happen. Similarly, if you're working in the comm space and you're doing some audio processing, well, now you have a bunch of elements over here that allow you to not have to start from the ground up building these things. There are many other tools inside of Simulink that specialize in one area or another. Some of them provide different modeling paradigms. So we saw earlier state flow, in which the lines were representing transitions between different modes of operation. There's also a modeling environment called SimScape, which enables you to model physical systems, physical machinery, be it electrical, mechanical, and so forth, and not at an equation-based level, but at a component level. So if you want to draw a circuit diagram instead of working out Kirchhoff's law, this would be the tool that you would use to pull that off. If you're not interested in modeling from first principles, then you have alternate approaches as well. There's the ability to perform data-driven modeling if you have a lot of data sitting around and you don't want to go through the hassle of modeling from scratch. The tools that would make that happen would be, one would be System Identification Toolbox, which provides black and gray box modeling capabilities based again on real world data or external data. There's also the Deep Learning Toolbox over here, which allows you some different neural network capabilities and so forth to build up representations based on pre-existing data. So you have your both options at your disposal, data-driven and model-driven or first principles. So we have a very rich environment when it comes to not only designing your system, but also for understanding and evaluating the performance of that system. The most obvious way to achieve this is that which we have already done. It is to go to your simulation tab and to run this model that you have constructed. In our case, we scripted up a scenario where the green object moved through a particular set of motions, and we were able to verify through inspection that the vehicle not only maintained stable flight, but was able to track that object and keep it within the camera's field of view. It is entirely possible for us to set up all kinds of other scenarios. We can try different sorts of objects with different movement patterns. We can also evaluate different designs. So what happens if we make the vehicle bigger? What happens if we change the control scheme slightly, or the sensor fusion algorithm? We can get very creative running different scenarios and making sure that the system is behaving as expected and satisfying those requirements. If you need to, you can make this process more formal than pushing the play button by hand. It is possible to invoke a Simulink model from the MATLAB command prompt with the sim command. There is also a command called parsim that is going to enable you to create a whole batch of simulations that you want to run. And if you have access to a parallel computing environment, run those simulations on your cluster or your multiple cores on your local machine. It's also possible to manage test cases very formally. We'll take a look at that when we get to the test and verification piece. Okay, but suffice it to say, our ability to simulate and evaluate how the performance of our system is playing out is something that we can very much do here. But it's not just simulation. What I want you to understand is that there are other tools at your disposal once you specify your behavior. What you need to do to find some of these things is you need to go over to your Apps tab, and inside of here you'll find a number of different tasks beyond pure simulation execution to evaluate your system. If you have the control system toolbox and Simulink control design, for example, you'll get access to all these specialized apps that deal with control analysis. If you have the fixed point designer, there is a fixed point app, and so forth. Many different apps that can help you further refine your system and make sure your design is working properly. For many of these, when you launch them, what will happen is you will get a new tab that will give you the ability to interact and perform those tasks. For example, Design Verifier has some capabilities when it comes to test generation for exploring logical pathways. It also has some non-testing or simulation-based analysis approaches, such as design error detection and property proving, to verify that a system is doing what it's supposed to without actually running the sim. So there are lots of different tools that are out there like this to further examine your system and understand what it's doing. And what you'll find if you drill into any of these is that you'll see a real consistent theme of reporting in addition to just execution of the analysis. You'll find in many cases that there are built-in reports that explicitly allow you to take all that work and export it into an easily digestible format for anyone who is responsible for inspecting your work and making sure that you're doing the right things. So reporting in addition to analysis is very much a theme you will find inside these tools. A very rich analysis capability, set of capabilities indeed. Okay, so hopefully that gives you a quick sense to what you get when you begin to specify your behavior inside of Simulink. From there, what you would do is once you're happy with what you built, is you would begin to move out of the Simulink environment and go into implementation. Now, what implementation looks like is going to very much depend on what you're building. What you will find is that for a very large number of groups that are embracing model-based design, that the implementation they're interested in is the software pieces of the program. And so model-based design is often affiliated with this conversion from a Simulink model into another language of software. Yes, you building software when you build a Simulink model, but that simulation can only be executed on a machine that is capable of running MATLAB, which means it needs to be the right operating system, have the right hardware resources, and have the right licensing capabilities. If you want to run what you've built in another environment, then you're going to need to get it out into some other language. And what I want you to understand is that we have ways of automating that process. If you are interested in converting your work into C or C++, we can do that with a tool called Simulink Coder and also Embedded Coder. That's the example we saw earlier. But if you're targeting other environments, such as an FPGA, we have a tool called HDL Coder that facilitates that. And if you're in the need of structured text for a PLC board, we have PLC Coder as well. So 4 different ways you can get your Simulink diagrams out into other languages. Why would you want to do this? Again, you may want to be moving to an environment that MATLAB cannot be run on. But before you even get there, it may be important to verify that as you move out of the Simulink model and convert to code, things are still behaving as you expect, that there's not something lost in the automated translation to these other formats. And so if you want to remain inside the Simulink environment and yet run your model as code or portions of your model as code, we have a couple modes that are available to you. We have a software in the loop mode and a processor in the loop mode, the latter of which either runs on your code on an emulator of your board or some other board connected to your desktop machine. But in all cases, once you're completely divested from Simulink, what you have is a royalty-free instantiation of your design. Moving up the design V now, let's say you want to get hardware involved. So first thing I'll say is that when it comes to hardware, we have the ability to allow Simulink to push and pull information from hardware during simulation. So if you're still over in your design portion of your process, but you have a need to stream data in from, say, a microphone or a webcam, or you want to push data out to some board that is connected to you via TCP/IP, that is perfectly doable. We can interface with hardware at that phase in development. But once you've got software, there also often becomes the question of, well, how am I going to get that software I've generated from Simulink out running on my embedded system? And for that step in the process, one way of approaching it is to take that on yourself and take the software we've given you and integrate it into your hardware on your own. That is not in the spirit of model-based design, of course. We want to tightly couple everything as much as possible. And so what we've done is we have provided a built-in support for a number of different hardware targets to make this transition from software down to hardware as painless as possible. The way you would begin to get access to some of those features would be to go over to MATLAB. And from within MATLAB, up on your tool strip here, you would find an add-ons tab. And that add-ons tab has an option for getting hardware support. What you'll find is a number of different results are available to you. Again, some of these focus on streaming data to Simulink or MATLAB while you're running in our environment. Others of them focus on deployment of your generated code to that board. So as an example here, I've already installed my Arduino support package, which if I go back to my library browser, I'll find listed here in my Simulink support package section. And you'll see a number of different blocks designed to make this conversion to the Arduino board easier. So really what you do is you add these blocks to the ins and outs of your behavioral design, and when you push the generate code button, provided you tell us where your Arduino board is, we'll not only generate the code with the proper, again, driver software, but also go ahead and export it out and begin to have it running on the Arduino or whatever other board you might be targeting here. So that is one way you can do this. There's sort of an intermediary solution as well that you should be aware of. These boxes here are from a company called SpeedGoat. SpeedGoat is a vendor that we partner with for our Simulink real-time solution. So Simulink real-time is the case where you want to take aspects of your model, you want to generate code for them and run that code in hard real time, but you still want to be able to make tweaks or evaluate how things are playing out from your Simulink environment. That is what Simulink Real-Time specializes in doing. It has the ability to target C code and HDL code for FPGAs onto these SpeedGoat boxes here. So check that out if you're interested in rapid prototypes or hardware-in-the-loop simulations. What about test and verification? So from the onset, we talked about having the need to develop a prototype to ensure that what you're about to push out the door is actually satisfying your requirements. Odds are that step in the process is not going to go away for you in a model-based design approach. However, we have hopefully woven a story for you that indicates that testing and verification does not begin in this phase in development. Really, in a model-based design approach, test and verification is an ongoing process that happens as soon as you begin to develop your requirements and architecture. We mentioned at the very beginning when we talked about architecture, the ability to do trade studies with MATLAB as the back end. Once you begin to put your components into Simulink and have your behavior, we just went through all the different ways you can simulate and evaluate that design. We have several different tools in the Simulink environment catering towards high integrity verification. So these are safety critical systems where a lot of documentation and robust analysis is required. For those kind of systems, we should check out our V&V product suite. I will show you quickly that what we can do when it comes to test management in a high integrity V&V process. So let me switch directories over here. I'll open up what's called an MLDATX file, and this will launch a tool called Simulink Test and the test manager within Simulink Test. So in this case, what we have is not just a person pushing run, evaluating what happens inside of Simulink, but instead a whole suite of test cases very formally defined and managed. So you can see here for requirement 2A, we have a test. If we're trying to test that mode logic we looked at with our digital thread example. We are hooking that mode logic up to another model inside Simulink, our test harness model. And if we need to make some overrides, well, we have a number of different ways we can override parameters, simulation settings, do post and pre-processing, a number of different things. And look there, we also have traceability back to requirements. So it's not just traceability to design components, but it's also traceability to specific test cases. There are a lot of good features inside of here, but the bottom line is that if you need to go very formal with your test management, Simulink Test is the tool to make that happen. And as I said, that is but one of several different verification and validation focused tools that we offer. Those tools work not only with model verification, but they often have tie-ins with code verification. So you can reuse those test cases that you built up with Simulink Test and begin to run them on processor in the loop testing or even hardware in the loop testing. We do everything we can, again, to help you find those errors earlier in the development cycle through continuous test and verification. Okay? So that is what I call the kitchen sink model-based design solution. That is everything we can possibly throw at you to make model-based design a successful process. For those of you that are new looking at this for the first time, you may be thinking, well, geez, that looks like quite a bit of work and quite a bit of learning required to pull all that off. How am I possibly going to do that? Or you may be thinking, that's all well and good, but I'm not trying to design a safety critical set of embedded software. Is model-based design still right for me in these cases? And I would answer that by saying yes, and I would tell you that model-based design is not an all or nothing choice. It's not a yes or no situation. There are really gradations of model-based design that you can choose to adopt depending on how much of your program you want to go into an MBD workflow and how much of different phases of your development actually need it. Our consulting service at MathWorks actually has a 6-pillar model-based design process assessment where they go through and look very carefully at someone's overall workflow and rate them on 6 different attributes. For me, I reduce that down to 2 principal components here to make it a little simpler. I really ask the questions, how much code generation are you doing? And how much modeling and simulation are you doing? Okay, those are really the 2 most important facets to a model-based design process in my mind. And as you see, you don't have to go straight to fully leverage model-based design like we just looked at. There are different tasks that you can perform that don't go to that level of complexity. And I'm not going to talk about all 8 other blocks inside this diagram here, but I do want to provide you with an explanation on a few of them, which I think are commonly encountered in aerospace and defense. The first one I'll talk about is what I refer to as the rapid prototype. So this is the case where you just want to get something out the door. You're not so concerned about making sure that you cross your T's and dotted your I's. So in this sort of workflow, you would have informal requirements. You would not bother with traceability for those requirements. You would probably skip System Composer and go straight into Simulink because your architecture doesn't warrant needing to go through the System Composer step. Your test and verification in the design phase will involve some tasks, but it won't be to the level of rigor of building up a test management suite inside Simulink Test or anything like that. Instead, you'll do some spot checks, make sure things work properly, and then once you're happy with what works properly, it works good enough, you'll push it out to hardware and you'll see what happens out in hardware. Okay, so it's all about getting to hardware as quickly as possible, which means skipping some steps. And yes, again, you don't get as much value out of model-based design in this approach, but there's still plenty of value to be had in doing this because of the automated transitions between these different phases of development. Variation 2 is the case where you really don't have any ambitions for embedded code, but you would like to take your work inside Simulink and get it out into some other framework. Okay, the picture you see in the bottom right is the logo for Trick. That is a NASA framework that you can find on Git. NASA Trick is a large simulation environment that they've been working on for many, many years, put a whole lot of IP into it. And there is no way that NASA is going to abandon that effort and transition everything they've done over into a Simulink framework. Instead, what you see people doing is they want to add to and supplement work that's been done inside of Trick by starting inside of Simulink, still leveraging all those analysis and verification capabilities in there. And once they're satisfied with things working, export their work into this other software framework. The way you would traditionally see this done is you would generate code just like we did before, but we are generating code now not with an eye towards getting it on an embedded system, but with an eye towards getting it into another software environment. So you get in that workflow, you can either choose to generate the code and worry on your own on how to interface that code with your other software. Or in the case of Trick, for example, we helped them build up a custom target that provided a more natural interface between what we generate for code and what they were expecting for a Trick module. So you can build custom, you can custom tailor your C code to more naturally integrate, or you can take it on by hand depending on what you choose. Another approach that you'll see is there is a tool called Simulink Compiler, which is available as of R2020A. Simulink Compiler is a way of getting yourself a representation of your Simulink model without the need to directly involve MATLAB in it. So it's royalty free. You don't need a license anymore. You can use a Simulink Compiler to tie your work into production servers, run things on clouds. You can do something called functional mockup units. So that's a standard way of integrating lots of different software components together. There are many ways with the compiler that you can do this as well. The idea, though, is that you're not directly working with the C code at that point. So both workflows are available to you if deployment to another software environment is your aspiration. Last but not least, let's move one up that no embedded code section of the grid and look at model-based design for non-software systems. So this is the case where you're really not building embedded code. You are instead building a piece of machinery, perhaps, something that is much more hardware focused and less embedded focused. So in a workflow like this, what you would focus on is you would focus on building a model that represents the dynamics of the real world. You would build a very high fidelity simulation that mimics what this machinery would be doing out once it's deployed. You would use this environment to make sure that the design you're proposing is going to satisfy the requirements of this, again, non-software based system. So you may try things like, what happens if I make the arm of this actuator a bit longer, or I rework the circuitry of this component, or I change this from a hydraulic system into an electromechanical system. Things like that is what you would be doing. Now, if you are going systematic V&V, what you would also be doing in this kind of workflow is you would be deriving what you're doing inside of Simulink from requirements. So you still would be using the requirements editor, still showing traceability to components and test cases. You would be creating very formal sets of test cases to demonstrate that you are on the right track for your system. The only reason you might generate code in this kind of workflow is you might do what I call a hardware in the loop test. And what I'm referring to here is the idea that you would take this high fidelity model you've built, you would convert it into code so that you can run it on a real-time operating system, which may interface with your hardware, pieces of hardware, or it may interface with the embedded software, the embedded system that was developed outside of Simulink. This is something that I did at my last job. It's a little bit expensive to run a launch vehicle experiment. And so what we would do instead of stressing our launch vehicles to the breaking point in the real world is we would run hardware in the loop sims, where we would trick that flight software into thinking that it was flying and stress it in a simulated environment to make sure it is satisfying its requirements. If you do all that, you should be confident in whatever you're building once you actually do implement it in the real world. And you have the fringe benefit of, once this thing is out in the real world operating, that you have this really high fidelity simulation just sitting around at your disposal. You can use that to do follow-on projects that are based on that design. You can use it as a starting place. You can use it to do predictive maintenance predictions. So if you need to evaluate when you need to take these systems offline and make sure that you're maintaining them before they fail, but doing that intelligently, you can run your simulations to learn what the beginnings of failure looks like. And that ties into the idea of having a digital twin. So if you want to run this thing for offline evaluations or run it in parallel with your real system, you have yourself a nice handy dandy digital twin. So a lot of good reasons to use Simulink, even if you have no ambitions for embedded software development. So that's pretty much it when it comes to the explanation of what model-based design is all about. Just to summarize what we discussed, model-based design is a well-established methodology for the development of a variety of systems in aerospace and defense. It's been around for a long time, and it's been applied to a variety of different kinds of systems. So feel confident in taking a look at it. There is value in model-based design, as we just saw, for large or small projects, or for some or all of your development cycle. Okay, again, it's not all or nothing. You can pick and choose strategically where you want to initially embrace model-based design, and perhaps from there you begin to expand it to other phases as it makes sense. And then finally, getting started is easy when it comes to model-based design, and we can help you out if you need some help getting going. To that end, I will provide these slides to you afterwards. They give some hyperlinks to some very useful resources. First are a couple up there for learning a bit more about the ideas of model-based design. There are lots of good user stories out there. We have a page as well dedicated to talking about solutions in the aerospace and defense world. My group is in application engineering, like I said at the beginning, and our whole job is to make sure you know what you're getting yourselves into. So if you have a particular project in mind and you'd like some personalized advice as to how to approach it, application engineering is a great group to begin that conversation. We can drill in more deeply into different facets of a development process. We can give you proof of concepts and going through guided evaluations to make sure you are confident in the pathway that you are about to embark upon. We can also help you ramp up, and we're happy to do that. But if you are one of those people that are like to learn on their own, we have lots of good resources for that as well. I've highlighted just a few hyperlinks for good resources to begin to get familiar with some of these tools. There are plenty of good videos that are out there on a variety of subjects. There are videos that drill into many of the different phases of model-based design that I was only able to scratch the surface of today. Moving beyond application engineering and self-service, if you would like to really become proficient with these tools, we have a couple other departments at MathWorks that can be useful to you. The first is MathWorks training. Our training department has a variety of courses related to model-based design. Those can be delivered on-site, virtually through an instructor live, or they can be done publicly out in a public environment. There's also self-paced training as well for several different classes. MathWorks Consulting, their job is to give you project-specific guidance. They are really there to help you get off the ground running and give you really tailored solutions, but they focus on not giving you a solution and letting you run with it. They really focus on making sure that you are self-sufficient after they leave. So that is really what our consulting business is all about. You see there we have things like the process establishment of model-based design, a specific framework designed to help new organizations adopt model-based design in an intelligent and efficient manner. So lots of good knowledge to be had with MathWorks Consulting as well. And with that, I would like to say thank you very much for your attention today.